Hello there. Today we're going to talk about exponential functions. Exponential functions grow or decay by the same percent per unit of x. So it's not a constant growth rate if we look at this exponential function, but the relative change is constant. So this grows by the same percent per unit of x. And what that means is x, as you get a bigger and bigger function, that percent is going to be bigger and bigger too, that amount. And so that's what we call exponential growth. So exponential functions have the form y equals a times b to the x. And a is the initial value. You could see a is the y-intercept. And b is called the base of the function. And the bigger b is, the more steep this growth is. So generally, if we have b is greater than 1, what we have is exponential growth. And then x ranges from negative to positive. So b bigger than 1 is exponential growth. Now, if you have b between 0 and 1, you have exponential decay. So decay means it's coming down from left to right. And this is for our base that's between 0 and 1, a fractional base. You have exponential decay. So b bigger than 1 is growth, b between 0 and 1 is decay. And if we're looking at growth, the bigger b is, the more steep you have your growth. So let's look at a few graphs of these. So here's a couple of graphs of some basic exponential functions. Here's y equals 2 to the x. Notice there is no a, so the initial value is understood to be 1. So that's why the y-intercept here is at 1. So 2 to the x, notice 2 to the 1 gives me 2, 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4. So this is 2 to the x. Now if I increase my base to 3, y equals 3 to the x, well, at the origin 3 to the 0 is 1, then 3 to the 1 power is 3. 3 squared is 9. So we could see that y equals 3 to the x is actually steeper, it rises more quickly than 2 to the x, because the base is bigger. Now there is a base in between 2 and 3 that's very popular, and that's called the natural base. And that natural base we denote with the letter e. And so here's a graph of y equals e to the x. Since e is in between 2 and 3, and actually e is 2.71828 and so on, and we'll see what e is in a moment. It's between 2 and 3, so y equals e to the x is in between y equals 2 to the x and y equals 3 to the x. And e is called the natural base. Now, what is e? E actually came about as a result of calculus. And it was discovered e was equal to the limit as n goes to infinity of this expression, 1 plus 1 over n to the n. So in other words, as you put in bigger and bigger values of n into this calculation here, you're going to end up with this number here. So a couple of things about e. E is an irrational number. So it is irrational. It's kind of like pi. It's a transcendental number as well. We call it transcendental. It goes on forever. No particular pattern. And interestingly enough, it's a naturally occurring base, and we'll see why e is used a lot in modeling population growth. So, and the name for e, why it's called e, it's named after this mathematician called Euler. And so it has the letter e to denote it. So e is a constant. It is this number here. And we're going to be using this number quite a bit. So let's look at the properties of these exponential functions. So here we have the basic exponential function, y equals b to the x. And the domain of this function, so here we have the basic exponential function, y equals b to the x. The domain of this function is going to be all real. So you put in any x value here in for x. And the range is y greater than 0. So notice it is never going to hit that x-axis, so y is going to be greater than 0. And that brings us to the horizontal asymptote. There is a horizontal asymptote, which is the x-axis. Now we're looking at the exponential growth function here, but the same applies for the exponential decay function, where b is now between 0 and 1. Well, you still have all reals is going to be your domain, the range is still going to be y greater than 0, and the x-axis will still be the horizontal asymptote. So that's our basic exponential function. Now what happens if we shift around these functions a little bit? So here's a graph of y equals 2 to the x, exponential growth function with base 2. What if we're asked to graph y equals 2 to the x minus 1? How does that affect this graph we have here? Well, remember from transformations, when you do something to the argument, to the x, you're going to shift it horizontally the opposite direction. So 2 to the x minus 1 is going to look just like this graph, but shifted to the right 1. So here's our graph of y equals 2 to the x minus 1, which is the same as the original graph, it shifted right 1. Now what happens if you to do a vertical shift? For example, supposing I want to graph 2 to the x minus 1 plus 2. Well, my original graph of 2 to the x is going to shift right 1, as we just saw with the x minus 1. But this additional 2 is going to shift it up 2. So if I shift the red graph up 2, we get the graph in brown here, y equals 2 to the x minus 1 plus 2. Notice all the points on the red graph have now shifted up 1. And now the horizontal asymptote of this graph is no longer the x-axis because we've shifted everything up by 2. The horizontal asymptote is now y equals 2. So once you shift it vertically, you're going to change the horizontal asymptote. So as we see, exponential functions are great for modeling population, and also it's great to model the growth of money with interest. So let's take a few applications of exponential functions.